Hello there, and welcome back to your next physics video lecture. This lecture, the reading that goes with it, is in Chapter 4 of Fundamentals of Physics, Section 4, and the topic is called projectile motion. And so what do we mean? That's the first important thing to get clear. Projectile motion is talking about when you take some object, maybe a piece of chalk, and you give it an initial velocity somehow, maybe by throwing it, or something more violent, like firing it out of a device or kicking it. But the point is you just give it an initial velocity and then let go. And the projectile motion begins from the moment it's let go until it lands or hits something. And the only influence during the projectile motion itself is gravity. We ignore air resistance, and there can't be anything else that's touching the object or pushing or pulling on it in any way. You just take an object, you give it an initial velocity, and then you let the only influence be gravity. Now, this initial velocity that we're talking about is not necessarily straight up like we would have done in Chapter 2, but up generally and at an angle. And so if we imagine horizontal axis and a vertical axis, then the initial velocity has a horizontal component and a vertical component. Like, for example, you might kick a soccer ball. The minute it leaves your foot, it has an initial velocity that has a horizontal component and a vertical component. And while it's moving through the air, if we assume the only influence is gravity, then we have projectile motion. That's the kind of situation we're talking about in this section, and really nothing else other than that specific scenario. But of course, there are lots of situations where you can have such a thing going on. You can kick a soccer ball from a soccer field. You could take a soccer ball up onto a tall cliff and kick it there. Or take a stone up onto a tall cliff and throw it horizontally and upward. Or maybe throw it horizontally and downward if you're on a cliff. There are many, many, many different scenarios that you can come up with, but they're all projectile motion, and the physics is all the same. So let's just start talking about the physics and how we're going to study projectile motion. So the first thing I show is a very simple coordinate system diagram that gets at some of the important information we're going to deal with. We're going to take the x-axis to be horizontal, either along the ground or parallel to the ground. We're going to take the y-axis to be vertically upward. If the ground is flat, then perpendicular to the ground. The origin O, of course, is where the x and y axes cross. And in this diagram, I have sketched the most straightforward application of projectile motion. A particle, say for example a soccer ball, has been given an initial velocity. It has just left the kicker's foot, for example. And it's then going to undergo projectile motion with the only influence being gravity. Let's focus for just a minute on this initial velocity that the soccer ball has been given. It is shown here in my diagram, if you look very carefully, at that red arrow right there, labeled, notice, I'll draw it over here to the side, V0 arrow, right there. That's the initial velocity vector. Notice it points to the right and upward, horizontally to the right and vertically upward. So it has a horizontal component, that'd be its x component, and a vertical component, that'd be its y component. And I've sketched both of those components. If you look very carefully, the x component of the initial velocity is along the x-axis, and the y component of the initial velocity is vertically up. And those components are labeled right below v initial x and v initial y, right there. Notice I've also given an expression for how you can calculate those numerical values of those initial velocity components. You need to know two things to calculate v initial x and v initial y. You need the magnitude of the initial velocity. That would be denoted v initial arrow absolute value. Just how fast was the soccer ball moving at the moment it left the kicker's foot? That will usually be in meters per second. That's the magnitude of the initial velocity. And you also need to know what's often called the firing angle, theta initial. That's just the angle that the initial velocity vector makes with the plus x axis. And again, down in our picture, though there's a lot going on, that angle is right there. That is the angle that v initial vector makes with plus x. So that would be given to you, usually in degrees. So if you know v initial magnitude and theta initial, then you can use these two formulas right here to calculate v initial x component and v initial y component. Magnitude v initial cosine theta initial for the x component, and magnitude v initial sine theta initial for the y component. So that is going to be important. What are the x and y components of the initial velocity? What other physics do we need to know to analyze projectile motion? Well, it turns out that one of the very important things to know, to understand or appreciate, is that the horizontal motion along x and the vertical motion along y, those two are completely independent motions. So what you really got is two one-dimensional motion situations going on, because the x motion does not affect the y motion, and the y motion does not affect the x motion. So here's a very important point then. The horizontal, i.e. x, and vertical, i.e. y motions are completely independent of each other. I want to demonstrate that to you with a video from Wiley Plus. And all I'm going to do is run this video, and it's going to show a device called a shooter dropper. And what it does is a simple little device. It's going to have two little cubes or blocks. And it's got a little lever. And when you release the lever, one block is allowed to just simply fall vertically down from the release point to the tabletop. And the other block is given an initial velocity by a kicking mechanism, and that initial velocity is purely horizontal, and then it undergoes projectile motion down to the same tabletop. So they go through the same y distance, but they undergo very different horizontal motions. The one that's dropped doesn't have any horizontal motion, and the one that's kicked has horizontal motion. And what the video is going to show is that even though their horizontal motions are different, their vertical motions are identical, because they are at the same vertical coordinate, the same y value, at any given time, including when they land. They will land at the same time. So let me show you vertical and horizontal motion shooter dropper. There's the device. There's the release mechanism. There's the motion. That was very fast, so here's slow-mo. The green one goes straight down. The orange one is a projectile. They are always at the same y coordinate at any given time, but very different horizontal motions. This is meant to show you that the horizontal motion and the vertical motion do not influence each other. They don't care about each other. Okay? You have to really just take two motions independently, x and y. Okay, now back to our notes. Let's look then at the horizontal motion first. Remember, the only influence is gravity. Gravity, as we know, is a vertically acting influence, right? There is no horizontal influence from gravity. Gravity doesn't pull you sideways. It only pulls you vertically down. So as a result, if there is no influence on the horizontal motion, the horizontal velocity component, the x component of the velocity, is constant. That is absolutely vital, so I'm going to even circle it as well as highlighting it. The x velocity of a projectile in projectile motion is constant. So, excuse me, pardon me why that little ring program interrupted me. Here we are back again. So that means that the x component of the acceleration is 0, right? Because if the x velocity is constant, then the derivative of the x velocity, dvx dt, is 0, and that is a sub x. So a sub x is 0. And therefore, the x velocity at any time is just whatever its initial value was, the minute it started its motion. So v sub x at any given time is just whatever its initial value is, v initial x. And we know how to calculate that. Magnitude v initial, cosine theta, pardon me, initial. And if we want to find how much its x coordinate changes with time, all we have to use is constant acceleration equation 2. I'll write it all out here for you. Delta x equals v initial xt plus 1/2 a sub x t squared. That's constant acceleration equation 2 for x motion. But drop the term with 1/2 a sub x t squared, because a sub x equals 0. And all you're left with is the very simple formula that to calculate the change in the x coordinate of a projectile during its motion, just take its constant x velocity times the time. And you're done with the horizontal motion. That's all there is to know. It's very simple. Now, the vertical motion is influenced, of course, by gravity. But that's just a free fall problem from chapter 2, where we know that the y acceleration then is constant, directed vertically down. So a sub y is just negative little g, our old friend little g, 9.8 meters per second squared, with a negative sign in front of that little g to denote that a sub y is down. But the a sub y is constant, so you get to use the constant acceleration equations, but now for y motion. So for example, constant acceleration equation number 1 for y motion, v sub y equals v initial y plus a sub y times t, but for a sub y, substitute negative g. And you've got a handy-dandy little formula for calculating v sub y in terms of t. Do you want to know how much the y coordinate of the projectile changes as a function of time? Use constant acceleration equation number 2. The change in the y coordinate equals the initial y velocity times t minus 1/2 gt squared, where again, for a sub y, I substituted negative g. Want to relate the y velocity to the y displacement, and you don't care about t? Use constant acceleration equation number 3 for y motion. V sub y squared equals v initial y squared minus 2g delta y. That's the physics. Constant velocity motion horizontally and constant acceleration motion vertically, with the acceleration equal to negative g. And if you can remember those two pieces of physics, that will go a long way in helping you understand and solve projectile motion problems. Now, the next thing to note is when you have a particle that's been kicked or fired or thrown, given an initial velocity with both a horizontal and a vertical component to that initial velocity, but then thereafter the only influence is gravity, that's projectile motion, what's the actual path that the projectile takes through the air? Look back up there at my picture, my sketch, in the xy coordinate system. Remember, the x-axis in this case is along the ground, so you can think of this as being the ground. At least for right now, let's just think of that as being along the ground. The y-axis goes vertically up. There you see the actual path that the particle would take. It's a curving path, rising up, vertically up, and traveling horizontally as well. It reaches a point that we often call maximum height, where the y coordinate is the maximum, and then it comes back down again. And the actual mathematical formula describing y versus x is the equation of a parabola. If you want to see that derived, read section 4 in chapter 4 of Fundamentals of Physics. But it's very well known that the path or trajectory of a projectile is, meaning the equation describing its motion in the y-x coordinate system is a parabola. Let me show you that with an animation. And now let me get to a Wiley Plus animation. Here you see an xy coordinate system. The x-axis is along the ground. The ground is kind of shaded tan, and the air is shaded blue. And the y-axis goes vertically up. And we have taken some little particle. It's going to be probably hard to see, but it's right at the origin right now. And it's given an initial velocity. And that initial velocity points up and to the right. It's represented by that red arrow with the open tip. And that initial velocity has an x component pointing to the right and a y component pointing up. And in the animation, you can adjust the value of those two initial velocity components. And right now, they're both, v initial x and v initial y, are both 20 meters per second. So this projectile is given this initial velocity with x and y components of both positive 20 meters per second. I'm just going to run the animation so that you can see it move through the air. The black curve is its path or trajectory. The black curve is a parabola. Let me just adjust the time slider so that we can see some of these vectors. The blue arrow pointing from the origin out to where the projectile is the position vector, r arrow. The red arrow with the open tip is the velocity. Notice the velocity is tangent to the path. And although it may be hard to see, let me adjust the time slider a little more. There's also an orange arrow that represents the acceleration vector. Notice it points vertically down. And then the other things to note is that the animation also shows the x and y components of the velocity at any given time by just regular red arrows. The x velocity points horizontally and the y velocity points vertically. Let's talk a little bit about what's happening to the velocity components as the projectile moves. So again, there we are at the initial situation. V initial x is to the right, V initial y is up. They're both at 20 meters per second. And the projectile starts to move through its path. Notice as it goes up, look at the red arrows that represent the velocity components. Look at the velocity component pointing vertically up, the red arrow pointing vertically up. As it goes along, as the projectile goes along, do you see that arrow is getting shorter? You see why? That's because v sub y is getting less on the upward journey. Why? Because the y acceleration due to gravity is down. So the y velocity is decreasing. Its vertical motion is slowing down on the upward journey. Now watch the horizontal velocity component, v sub x. Notice very carefully that the v sub x arrow is not changing its length. V sub x, remember, is constant. The horizontal motion is at constant velocity, constant x velocity. That's very important. Let me try to get as close as I can to the high point. It's right about there, okay? The high point of the trajectory. Here's a question for you to ponder. What is the projectile's velocity at the highest point? Maybe you should pause the video and think about that for a moment. Get an answer in your head. What is the projectile's velocity when it's at its highest point? And then come back. Okay. So, what is a projectile's velocity when it reaches the highest point in its trajectory? I will tell you that there's a very strong temptation to say that the velocity is 0. But that is not a good enough answer. In and of itself, just to say 0 is definitely just not correct. Here would be the correct answer. At the highest point, the y component of the velocity equals 0. But remember, the x velocity can never change during the motion. The x velocity is constant. And since it had an initial x velocity of 20 meters per second, it must still have an x velocity of 20 meters per second at the highest point. So the best answer to my question, what is the projectile's velocity at the highest point in its motion, would be v arrow equals 20 meters per second times I hat. Aha, I gave it to you in unit vector notation, didn't I? I hat because it's an x component only. Now once you cross over the highest point and start the downward journey, now look what's happening to the y velocity, represented by the downward pointing red arrow. It's getting longer. That means the y velocity magnitude is increasing. Its magnitude is increasing, but it's negative. So the y motion is speeding up downward. Remember, the x motion is always at constant x velocity. Okay? Okay, that's kind of the simplest example of projectile motion. But note there are all kinds of variations on this that are really, as far as physics is concerned, the same problem. Like, what if you take the object up on top of a building to a height, an initial y height of, say, y initial of 10 meters, and give it the same initial velocity? What will its motion look like? Let's run it. Well, it starts at y equals 10 and goes through a parabolic trajectory, and now it lands down on the ground. Okay? Or, what if I take it up to that initial height of 10 meters and throw it completely horizontally, so that v initial x is 20 meters per second, but v initial y is 0. Can you visualize what the trajectory will be now? Think about that for a second. Ready? Let's run it. It's still part of a parabola, but now it starts out with the initial velocity completely horizontal, and then it starts to curve down towards the ground. So these are all, as far as a physicist is concerned, the same problem. You just have to keep track of those details. Okay? Okay. Let's now continue with our slides. I want to point out one handy little special case that can be useful in solving homework problems. I'm normally not a fan of just taking what I call a canned formula that's been derived already by the book, and I just grab it like it's some mysterious box that I don't really know what's going on inside, but I'm going to use it. I don't normally like that kind of approach in physics, but this one's handy sometimes, and I want to talk about it. It's in a situation where you are asked to find what's called the range of a projectile. First, let's be clear what we mean when we ask for the range. We mean the horizontal distance traveled when the landing and the firing points are at the same height, the same y value. The starting y value and the ending y value of the projectile motion must be the same. Then the horizontal distance traveled from starting point to ending point is called the range. This new picture I'm showing you is an example of what I mean. We've got an xy coordinate system with plus x to the right along the ground, plus y vertically up. Somebody fired a projectile from the origin with an initial velocity. It's represented by the blue arrow, v initial. That's tangent to the parabolic trajectory at the initial point. And that initial velocity is at a firing angle theta initial. And then you see the red curve is the parabolic trajectory, and this projectile happens to be going up and over a brick wall. And so it was fired at point A, it goes up through point B, point C is its highest point, it comes down to point D, and it lands back on the ground at point E. Note the horizontal distance traveled from point A to point E, firing point to landing point. Just the distance there is what is denoted by capital R, and that's called the range of the motion. If you read this section in your book, which I recommend you do, you will see that your author derives a formula for calculating this range. There it is. And as I said, it's handy if used correctly. The formula is, for the range, take the magnitude of the initial velocity squared times the sine of 2 times the firing angle, and divide all that by little g. So watch out for that formula. It's handy, but you got to use it correctly. The v initial is the magnitude of the initial velocity in meters per second, and you got to square that. And inside the sine, you've got to take whatever that firing angle theta initial is and multiply it by 2, and then take the sine. And of course, when it comes time to plug in the g, you plug in our old friend, positive 9.80 meters per second squared, and that will give you the range. Again, handy if you use it correctly. So here's the tip to watch out for. Be careful not to use the range equation in situations where the landing and the firing points are at different heights. If you have a problem where the landing point and the firing point are at different y values, and yet the problem asks you for the horizontal distance it traveled from firing to landing, you can't use the r equation. Let me show you this picture right here, what I mean. Very typical scenario. Somebody has taken a projectile. You can see the axes there, x and y, x to the right, y upward. The particle, there it is initially, was fired from the origin. The dashed line is its parabolic trajectory, but it lands up on some kind of elevated plateau. So the firing point and the landing point are at different y values. But the problem may very well ask for the horizontal distance traveled. That's just the horizontal distance from the initial point to the final point. Don't use the range equation. That's my emphasis. How would you find the horizontal distance traveled? Easy. We know the physics for the horizontal motion. Delta x is v initial x times t. Take the initial x velocity. You'll have to be given enough information to find the travel time t, the time from firing to landing, and that's how you get delta x, the horizontal distance. Okay, the last thing in this video is a little bit of a class engagement exercise that I'm going to want you to complete and put your answers on Blackboard. Let me describe to you the situation. It's that same picture I was just showing you. There's a horizontal x-axis and a vertical y-axis, and a projectile is fired initially from the origin of that coordinate system at the point labeled A, and it goes up and over a wall. And you can see the red curve is its parabolic trajectory, and we've labeled particular key points in that trajectory A, B, C, D, and E. Just like I showed you in the previous slide. Okay, here comes what we want you to do. We're going to give you 5 expressions for the velocity vector, meters per second, of our projectile. And you can see them below down there, 1, 2, 3, 4, 5. They're all expressions for the velocity vector. They happen to be given in unit vector notation with an x component and possibly a y component. You can see all the expressions there. Okay? For example, in expression 1, we're talking about a situation where the velocity vector has an x component of positive 13.5 meters per second and a y component of negative 16 meters per second. So that's just to make sure it's clear to you what this notation means. Here's what we want you to do. Match the number of each velocity vector with its corresponding letter on the path. For example, velocity number 1, v arrow equals 13.5 I hat minus 16 j hat. Which of the lettered points A, B, C, D, and E on the trajectory, at which of those points is equation 1 the correct one for the velocity? Then go on to equation 2 for the velocity. V equals 13.5 I hat plus 10 j hat. Which lettered point, A, B, C, D, and E, corresponds to that velocity? Okay? And I want you to put these answers on Blackboard. Just write your answers. In other words, with 1, you write a 1, and then you put a letter beside it, A, B, C, D, or E. Then 2, and a letter, A, B, C, D, or E, and so forth through 5. And that's what I want you to do for your class engagement for this video. We will talk in class about projectile motion, so we'll have more chance to practice then. But that's all now for this video.